Okay, welcome back. So far we've seen that multiplying a row by a constant results in multiplying the determinant by a constant. That move, or that realization, allows us to factor a constant instead of rows and factor a constant instead of columns when we're doing determinant calculations. So it gives us an accounting rule for that type of row operation. The second experiment, or set of experiments that we did, it revealed that when we perform the elementary row operation of a swap of two rows, and it works out, it's the same for the swap of two columns, the determinant picks up a negative sign. And if we do it twice, it'll pick up the multiplication by two negative signs, which results in no change. If we do it three times, we do three row swaps, we'll pick up a negative times a negative times a negative, which is going to end up being a negative, and so on. There's one row operation left, and that's the replacement of a row by itself plus or minus a multiple of another row. So we can do a one-off experiment. Let's start with the matrix A, 1, 2, 3, 4. Calculate its determinant. Determinant of A, down products minus up products, 1 times 4 minus 3 times 2. We've done this one a few times. 4 minus 6, so we get negative 2. And then see what happens if we replace, let's say we make that top left leading one happy, if we replace row 2 by row 2 minus 3 times row 1. Now take the determinant of that row reduced, or partially row reduced matrix. So what is the determinant of B? Is there any change? Is there any cost to this type of move? Down product, 1 times negative 2, minus up product, 0 times 2. Get negative 2 minus 0, which is the same. So it looks like, based on one experiment, that this is a free or zero cost move, that we can replace a row by itself, plus or minus multiple of another row, and there is no change to the determinant. We don't even need to keep track of it, other than to make sure we don't screw up the matrix. A single shot experiment makes no sense in terms of building confidence or building trust in a mechanism. Imagine a clinical trial with one patient, or imagine a psychology experiment with just one person in the study. You would never trust that. You wouldn't say, well, yeah, you can generalize that to 1 million people. In math, it's even worse, because there aren't a billion or 10, even 10, like whatever is it, 7.5 billion? Like there's more matrices than there are, like there's an infinite number of matrices. If I show you that something works for 100 billion matrices, that does not mean that someone else can go off and find one that will violate the rule. There's just an infinite number of these things. So you can't brute force the proof of something like this by just doing billions and trillions of examples. But I'll show you how to do a proof. A general proof on what the construction requires. I'm only going to do a 2 by 2. You can look at higher if you want, but just 2 by 2. I'm going to leave the entries general. Instead of putting numbers, I'm going to put A, B, C, and D. And I'm going to make the row operation general as well. I'm going to replace row 2 by row 2 minus K times row 1. So row 2 was C, D. Now it's C minus K times A and D minus K times B. If this property holds, then what I'll be able to show is that the determinant of this new matrix, capital B, is the same as the determinant of the matrix, capital A. If there's a cost to that move, that cost will be reflected in the value of the determinant that I find. So let's see what happens. Let's see what this is not an experiment. Let's see what this proof shows. Difference between an experiment and a proof. Determinant of A is equal to AD minus CB. Down products minus up products. Now let's do the determinant of capital B. It's down product, so A times D minus KB minus up products, B times C minus KA. So I have AD minus, distributing through the bracket, AKB minus BC plus negative times negative positive, so that negative B is multiplying through the bracket, negative B multiplied by KA, so positive BKA. Keeping in mind that these four quantities are all scalars. And order of multiplication of scalars does not matter, which is a property that We don't realize how nice it is until we find an object like a matrix where the order of multiplication matters. And even a vector for cross products, u cross v is not the same thing as v cross u. So we now we look back at numbers like, oh yeah, that's a nice property that I can just say AKB is the same as BKA. That I have a positive one and a negative one, they're going to destroy each other. And that the order of multiplication of B times C is the same as C times B. So AD minus CB, it's the same, no change. This is the determinant of A. So this move is free. This move has no cost. We can replace a row by itself plus or minus a multiple of another row, and the determinant is not sensitive to that change. The determinant stays exactly the same. If you're a glutton for punishment, if you really have so much time on your hands, you have nothing better to do than to show with a cofactor expansion for a general matrix n by n. If you do a cofactor expansion to calculate the determinant, that a row operation like this one, replace a row by itself plus or minus a multiple of another row, show with that cofactor expansion that there's no change. Now that's a harder calculation than this, but the spirit of it is the same. So I'm looking at this matrix here. We're asked to find its determinant, and we have a few moves that are available. I mean, we have the secret method. So this is a 3x3. It isn't that bad just to calculate it out. But I want to show you the property that we just explored. I want to show you that property in action. So even easier than the secret method is if we can convert this into a triangular matrix. So that's the goal. Convert into triangular. And how can we do that? So the first row can stay where it is. The second row can probably stay where it is. The third row, I need this to be 0, 0. Well, that -2 and that -4, I have to turn those to zeros. And then I don't care what happens where that 1 is. Whatever number is there, it doesn't matter. It's just going to be a number, and then the determinant will be the product along the diagonal. So how do I make that -2 disappear? How do I make that -4 disappear? And it's relatively easy. What happens if I replace row 3 by row 3 plus 2 times row 1? So this is equal to, I'm going to put the row 3 gets replaced by row 3 plus 2 times row 1. This is a free move. Has no cost. So it'll be the determinant of 1, 2, 3, 0, 5, 7, and then -2 plus 2 times 1, 0, -4 plus 2 times 2, 0, 1 plus 2 times 3, so 1 plus 6, 7. And now it's triangular. So we'll have 1 times 5 times 7, which is 35. The value of the determinant. That's a nice shortcut. All right, here's another one. Find the determinant of A. And I mean, if I was in a test, I wouldn't bother messing around with a 3x3 because we got the secret method. If we didn't have the secret method, if all we had was cofactor expansion, I'd be all over the idea of row reduction. I'm going to row reduce for that reason, just as practice for 4x4s. So I want this to be triangular. Goal, get to triangular matrix. That's the quickest way to get to a nice determinant property. So determinant of A equals the determinant of, and I'm going to do this row operation. I'm going to make sure I use some good notation here. Determinant A. Okay. So determinant of, I'm going to replace row 3 by row 3 minus 2 row 1. It's not going to make it as nice as the last one, but it'll be a start. This is a free move. There's no cost. Determinant does not change when we do this. So we have the determinant of the row 1 stays the same, 1, 1, 1. Row 2, 0, 1, 1. Row 3, 2 minus 2 times 1, 0. 5 minus 2 times 1, 3. 3 minus 2 times 1, 1. All right, and now it's not quite ready. I have to get rid of that -3. That -3 has to turn into a 0. I'm not fully row reducing the matrix. I should emphasize that. You can if you're desperate to. If you want to turn this into the identity matrix, go right ahead. Just make sure you do all the accounting properly, factoring constants out and doing swapping rows. Make sure you account for all those things. But if you're looking for a faster method than that, make it upward triangular. So I just need to zero out that 3 and it's upward triangular. So to do that, I'm going to replace row 3 by row 3 minus 3 row 2. So that's the move. It's a free move. No cost. No change to the determinant by making that modification of the matrix. 1, 1, 1, 0, 1, 1, and then 0, 0, 1 minus 3, -2. Now it's triangular. So we can say the determinant is 1 times 1 times -2, which is -2. And really quickly, I've got 3 plus 2 plus 0 minus 2, 0, 5. So 5 minus 7, -2. So same answer using the secret method. Secret method's faster, less writing, but if you're working on a 4x4, there is no secret method, and this method, the one that's on the slide, will work. All right, so put it all together now. We have all the row operations covered. We know how the accounting rule works for them. That if we swap 2 rows, they get a minus sign. Or actually, if we swap 2 columns, we get a minus sign to the determinant. If we multiply a row or scalar by a constant, that's going to change the determinant by the same amount. So we use this as a factoring type move. Factor constants out of rows and factor constants out of columns, put them in front of the determinant. And then replacing a row by itself plus or minus a multiple of another row, that's a free move. We can do that as much as we want. We don't have to keep track of the change to the determinant from that because there is no change. So this is related to row reduction, but it's like there's an extra bookkeeping or accounting step. We have to keep track of every time we factor something out of a row, we have to keep track of how many times we do swaps. And again, there's no need to bring the matrix entirely into reduced row echelon form. We can just bring it into triangular form, upper triangular form, even lower triangular form if that's easier, so that we can get access to that shortcut. All right, here we go. When you don't have the secret method, Uh-oh. There. When you don't have the secret method, what are you going to do? You're going to use these shortcuts. We're told that this matrix A, full of letters A, B, C, D, E, F, G, H, I, has a determinant of 5. And we're asked to find the determinant of these other matrices. So our goal is to convert each of these into the matrix A using row operations. Goal, convert each matrix into A using row operations. Okay, so the first thing I see is I'm going to take a 2 out of the first row. So a 2 will come out of row 1, and I take a 3 out of row 3. And I will have the determinant of D, E, F, A, B, C, G, H, I. And we don't quite have matrix A there. I can't replace that with a 5. I need to do one more thing, and that thing is I need to do a row swap. I can swap row 1 and row 2. So -1 times 2 times 3 times the determinant of A, B, C, D, E, F, G, H, I. So I'm going to label all these moves. This was from row 2. The 3 was from row 1, I mean, from row 1. The 3 was from row 3. And the -1 was row swap R1 with R2. So now we have -1 times 2 times 3 times the determinant of A. So -1 times 2. So I'll multiply those all out now. -6 multiplied by 5, we get -30 as the answer. Okay, the next one. I want to get rid of that minus sign. That minus sign is bothering me quite a bit, so I'm going to factor a negative out of that row. So equals -1 times the determinant of G, H, I D minus 2G Well, this has a typo in it. That 3 is supposed to be a 2. My apologies. Otherwise, we're in big trouble. So minus 2i. And then hi. And then ABC. So all I did there was I took the minus sign out of row 1. Next, I want to get rid of those -2g, -2h, -2i. So what I'm going to do is I'm going to replace row 2 So this is a free move. We're replacing row 2 by row 2 plus 2 row 1. So doing that type of move doesn't cost us anything. So I have G, H, I, D, E, F, A, B, C. And now we're going to do a row swap. So -1 times another -1 times the determinant of A, B, C, D, E, F, G, H, I. So that second minus sign came from a swap row 1 and row 3. And now we have the determinant of 1 times the determinant of A, which is just 5. Okay, now the last one. So we have to struggle to make this last one look like the first matrix. Make the C, 3B, -2A. How are we gonna do this? So first thing I want to do is I want to get rid of those constants. I'm going to factor constants out of the columns this time. So this is going to be a 3 times a -2 times the determinant of. I'm going to change colors for this one because it's gonna get a little bit messy if I don't. It'll be hard to tell what's happening from the other ones. So equals 3 from the second column. I'm going to take a -2 from the third column, multiply by the determinant of what's left. So C, B, A, F, E, D, I, H, G. So I'm looking at things that are the same and things that are different. There's a BEH in the second column and a BEH in the second column of A. So that's right so far. If I swap any rows, that's going to be wrong. So I can't swap rows, but I can swap columns. What happens if I swap column 1 and column 2? Well, it picks up a minus sign because that's the cost of a column swap. But then it also brings us to the matrix A, which is the goal. So we have 3 times -2 times -1 times the determinant of A, D, G, B, E, H, C, F, I, which is 6 times the determinant of A, which is 6 times 5, which is +30. And I'll label those moves where they came from. So the 3 was column 2 factor. The -2 is a factor from column 3. And then this -1 here was a column swap. We need to swap column 1 and column 3, which has a cost of -1. And we'll continue in the next video.